Raghunathan from Stanford joining us. She's the fifth year PhD student advised by Percy Liang. Her research focuses on building robust ML systems that can be deployed in the wild. She's a recipient of the Open Philanthropy AI Fellowship and the Google PhD Fellowship in Machine Learning. She has done some phenomenal work in trying to understand adversarial examples and just generally adversarial robustness. So today she's going to talk about trade-offs between robustness and accuracy. So before I pass the mic on to her, I would like to make some basic comments. So please keep your questions to the chat. I will be moderating them and asking Aditi during the talk. And later at the end of the talk, we'll allow people to unmute themselves and ask their questions. Okay, so Aditi, you can take over.
Okay, thanks Surbi for the kind introduction, and thank you to the organizers for inviting me here. And I'm really excited today to be talking about some of our recent work on trade-offs between robustness and accuracy. This is joint work with my fantastic collaborators at Stanford, Michael, Shiori, Pangwei, Fanny, John, and Percy. Okay, so the general robustness problem is concerned with a setting where the train distribution and the test distribution do not match. So you can have various robustness definitions where the train and test distributions are related to in different ways. But by most of these definitions, current ML systems are actually quite fragile. So one broad category of how the training test distributions could be different is the one inspired by robust statistics, where your training data could be corrupted and could have outliers, but you test on like sort of normal instances from your underlying distribution. In this talk, we'll be focusing on the other kind of setting inspired by robust optimization, where your training data comes from the underlying distribution, but your test instances are hard. In other words, we test the model on harder inputs to sort of inspired by the setting that when we deploy a trained system in the wild, we do not have complete control on what the inputs could be to this system. And in particular, I'll be focusing on two different problems under this framework. One is that of adversarial examples, and the other is a problem where models could rely on spurious correlations. So very briefly, adversarial examples. So this is a very prototypical example, which sort of led to adversarial examples gaining a lot of attention in recent times. So here's an example where the input is a panda on the left, and as you pass it to an ImageNet classifier, for example, it's classified correctly with like reasonably high confidence. And this is an example of a normal test input that the model does well on. However, when you make the input harder, by adding this carefully controlled noise, even though it's a very small magnitude, you get this image on the right, which looks basically the same to humans, but then you can fool your classifier into thinking it's a gibbon with like even higher confidence, for example. And it's not just this one particular sort of panda, and in fact, this is quite easy to find adversarial examples. For example, on the CFAR10 image classification task, we do really well on sort of normal test examples, like an off-the-shelf wide ResNet that we train would get 95% accuracy, but almost all these examples, it's very easy to sort of perturb them in a very small way to get imperceptibly similar examples, but then the accuracy is basically 0%, so it's very easy to fool the systems, and they break catastrophically in presence of these small, carefully controlled perturbations. So this is like one problem of adversarial examples and how we generate harder test inputs. The other problem that I'll be talking about today is relying on spurious correlations. So here's an example of a chest X-ray that is input to an ML model, and the model is asked to make a prediction on whether it has a collapsed lung or not. And the model predicts that this example has a collapsed lung. However, so this model actually does quite well on average, and the prediction would match the true label on most of the examples, and you get it right, and it looks like the model is actually performing really well. However, on more careful inspection, we see that there is actually a spurious correlation, which in this case is this chest drain, which is in fact a treatment for collapsed lung. So most of the examples of the chest X-rays where the lung is collapsed also has this treatment of chest drain. And it turns out that the model is actually using the spurious correlation to make the prediction because it has very poor accuracy on the demographic of untreated patients which have a collapsed lung but no spurious correlation present. So this is highly unsatisfactory because this is exactly the demographic that we want to use the system for, because we want to treat people who haven't been treated. And on this harder demographic where the spurious correlations are absent, the models perform quite badly. So these are two examples of how the harder test examples can actually make your system break quite easily. And here's a brief summary of sort of what are the kind of results that we'll be going into in this talk. So one observation from the setting of adversarial examples is that when we try to increase the robustness by performing some kind of augmentation where we add perturbations of the training example back into the training set and train your model to be robust, surprisingly, your standard error actually increases. So this is contrary to the wisdom of the data augmentation, where typically it improves the performance. But in the context of adversarial training, we see that actually adding data makes a model perform worse. And so this is also bad from a practical standpoint because we want the models to be robust, but if it gets worse at the task you care about itself, then that's not clear why you would want to use the system at all. The other sort of surprising observation is from the spurious correlation setup. So typically, as we increase the model size, we know that, for example, the normal CFAR10 accuracy typically increases as we increase the size of the model that we use to train. However, when we look at methods that try to increase robustness to spurious correlations, the opposite is true, in that as we increase the size of the models and make them bigger, they get less robust to spurious correlations. And in fact, they start using spurious correlations more as we increase the size of the model. So this is in stark contrast to what we know for standard accuracy, where bigger models are typically better. So the error on the subpopulation of untreated patients actually increases as we increase the model capacity, in this case of spurious correlations. So these two observations are interesting because one, it says that robust and standard accuracy do not always track each other. So a model could sometimes be more robust but less accurate. And also, things that we know are common wisdom from standard accuracy, which is that more data and bigger models are usually help in that setting. But in the context of robustness, they do not always help. And we might have to rethink sort of these common tricks that we use for training accurate models in the context of robustness. So the overview, so I'll start with sort of formalizing the setup of adversarial examples and present the main empirical observations that motivate the study. And we try to replicate these simple observations in a, replicate the empirical observations in a simple model that allows us to mathematically understand what's going on. And it also inspires a fix. And then we kind of take this fix and generalize to the empirical setting of, say, deep networks and see whether this actually works. And sort of similarly for the spurious correlations, just like formalize a setup, study a simple model, and then try to use this model to gain insight into how to solve this in practice. Okay, so with that, I'll jump into more details with the first part of the talk, which is focused on adversarial examples. This is based on work that appeared at ICML this year with Michael, Fanny, John, and Percy. So here's the formal setup of adversarial examples. So what we usually measure in machine learning is the standard error. So over instances that are drawn from the distribution, we check whether the output of the model f of x matches the label y. And we report the average error as like the percentage of instances where they do not match. So in robust error, we're not just interested in f of x, but rather in f of x tilde for all perturbations x tilde in a small ball around x. So the most common example of this ball is the L infinity ball, where you perturb each coordinate by some small quantity epsilon. So we measure error not just on the inputs x, but also on perturbed inputs x tilde. And we say that the robust error is the percentage of inputs where there is no adversarial perturbation that can fool the model. So when we want to train a model to get low standard error, what we typically do is we try to find a function that optimizes the standard error on your training data, for example, empirical risk minimization. And sort of a similar strategy says that when we want to do robust training to decrease the robust error, we just try to do that on the training set, and we find a function f to like approximately optimize the robust error on your training data, just similar to ERM, which is for the standard error. So this is the sort of setup of adversarial examples where we're interested in both the standard and robust error. And in particular, we'll be focusing on the two training algorithms, one that just simply minimizes the standard error on your training data, and one that minimizes the robust error on your training data. So like I said earlier in the slide, so robust training increases standard error. So here's an example. Let's consider the CFAR10 data set. And we have standard training, like I said, like basically has 0% robust accuracy, but it's quite accurate on average. It has like 95%. And here's an adversarial training algorithm in recent work by Zhang et al. And it is quite good in increasing the robust accuracy to like 55%, but quite unsatisfactorily, the standard accuracy decreases by over 10% and is now 84% compared to the original 95%. So robust training, by like say adversarial training, increases your robust accuracy, but also decreases your standard accuracy. So in fact, like we're not the first people to make this observation. A lot of prior work has also sort of observed that robustness and accuracy are at odds and tries to give an explanation for why this could be true. So if we understand why this could be true, we could then try to, like, for example, try to find a fix. So one explanation could be that the optimal predictor in terms of accuracy, so the one that gets like really high accuracy, might itself not be robust. So what this would mean is, let's say if we had an input example, like say the 0, and then we perturb it to now look like a 9, so this can lead to a conflict, because if you want to be robust, you want to give the same label, that is say 0. But then if you want to be accurate, like we know this is actually a 9. So in the case where the perturbations could actually change the label, clearly there is a fundamental trade-off between the two objectives, because one of them is predicting a different label than the other. However, these are not typically the examples that we care about in practice. Like for example, the panda, or like this MNIST example, we care about settings where we perturb 0 to something that's clearly a 0, but just has, say, some extraneous noise. And so both the robust and accurate label do match according to the humans. And so like there's fundamentally no conflict on this particular example. So you can be both robust and accurate. And the term that I would use in this talk for these kind of perturbations is like consistent perturbations, where according to the ground truth, the label is actually preserved across the perturbations. So when this is true, there is no real fundamental conflict in terms of the optimal predictor not being robust, which is majority of the kind of examples that we see in practice. The other explanation could be that the hypothesis class itself is not expressive enough to contain both robust and accurate predictors, even if that exists. So for example, let's say we only had linear classifiers, but then your robust, like when you perturb, you take the blue point here and the orange point here. So there's no way you can be like robust and accurate within the class of linear classifiers in this example. However, this also does not capture the full picture, because typically in practice, we use really big neural networks that we believe are expressive enough that they can represent arbitrary functions. For example, even on random labels, they're able to fit. So you can express arbitrary functions. Also, the training error, like both for robust and standard accuracy, is basically 0. And so this says that we have neural networks that are expressive enough to contain both a robust and accurate predictor. And in this talk, we basically focus on well-specified models, which we believe like kind of explains, which captures a really large neural network that can express any function. So if things are consistent and well-specified, like why is there still a trade-off? That's sort of going to be the focus of this talk. So another way to think about it is the following way. So is this trade-off between robustness and accuracy inherent? So the prior hypotheses, both of them suggest that the trade-off is inherent, either because there is no function or the function does not exist in your hypothesis class. And even with infinite data, you basically would not be able to overcome this trade-off between robustness and accuracy. But like we said, for the reasons before, these assumptions probably do not hold in practice, and it does not capture the entire picture. To further test this, we do an experiment where we plot the trade-off, that is the difference between standard and robust training, standard accuracy, as we increase the the size of the label data. So on CFAR10, we kind of generated different fractions of label data and plotted what the trade-off looks like as we increase the amount of label data. So as we see on the picture on the right, as we increase the amount of data, the trade-off actually shrinks. So the gap goes down, and it sort of says that maybe if you had infinite data, there actually could be no trade-off. And sort of this is true by definition if we assume consistent perturbations and a well-specified setting. So if there is a robust classifier and accurate classifier in your function class, if you had infinite data, you would find that classifier and hence be both robust and accurate, and there would be no trade-off with infinite data. However,
there is a clarification question in the chat. The question is, what is robust training? Is this terminology the same as adversarial training?
Right. So yeah, so in the literature, for some reason, adversarial training is associated with a particular way of minimizing the training error, the robust error on your training set. By robust training, I mean like the adversarial training, like for example, by Madri et al., but also things like trades, which slightly modify the loss function, but basically it tries to have a different proxy for the robust error on the training set. So all of these methods basically have the same principle of reducing the robust error on the training set. And I think of all of them as robust training in this talk.
So robust training is more general than adversarial training.
Yeah, but it's slightly, it's only slightly more general. For example, like trades has a slightly different loss function, but it's basically like, it's like adversarial training.
Mm-hmm. Thank you.
Yeah. Yeah, you could also consider things like certified training as robust training, and they also exhibit the same phenomenon where you try to do some convex relaxations, like a different proxy for the loss. And even there you have the same observations that the accuracy falls. But like if people are familiar with adversarial training, you can basically think of robust training as adversarial training. Okay. Yeah, so just to sort of summarize again, under the setting of consistent perturbations and well-specified setting, there is no trade-off with infinite data, but the trade-off manifests with finite data. And so this is interesting. So why does like this trade-off manifest with only in the finite data setting? So here's a simple example. So let's consider the simplest possible setting of regression by our splines. And like before, we make this assumption that things are consistent and it is well-specified. So surprising. So this was quite surprising to us at that point, where you can get a trade-off even in a convex setting with finite data. So in some sense, as you do robust training, what you're doing is adding constraints to the training set, which are actually true of the classifier f theta star. So it feels like you're only increasing the amount of information available to your algorithm. So then why would it actually affect your generalization? So this was quite surprising to us. But here's a sort of picture that could capture what's going on. So here, suppose we had a staircase kind of f star, which is picturized over here. So this is your true underlying function. Now, let's say you had the standard data, which was a few points from the line. And now if we only fit these points, which are in purple, we would get this blue standard estimator, which basically does quite well and obtains low error overall. So it has a good standard error. However, now when you try to make things robust, by adding these perturbations, so along these perturbations on the staircase, we know that the function value is preserved. So if we try to add this information to the training set, what happens, for example, when we fit the splines, say we had only 4 points in the training set, like as it fits the robust points, it extrapolates quite badly off the on the rest of the line, and your standard error is higher than what you would have got if you just simply didn't incorporate this extra local information. So this is an example of how adding specific information, which is true of the underlying function, could still make generalization worse. So sort of one way to think about this issue is that we fit a local structure when you try to do robust training, and this could come at the cost of a global structure, which might have been better captured by just doing the standard training without including these perturbations. So this could be one issue as to why, even in like a well-specified setting with consistent perturbations, with finite data, you can have this problem. So of course, if you had infinite data and saw the entire staircase, you wouldn't see this problem. So there is no trade-off in infinite data. But in the finite data, both these estimators could behave quite differently. So think of this sort of in a more mathematical setting. Let's consider a general sort of linear regression. So we took the simplest possible model that still exhibits this phenomenon, which is like, let's say we do noiseless linear regression. So y is just x transpose theta star, and this is well specified. Let's say we had some standard data, which we denote by x standard, and we are focused on this overparametrized regime where the number of data points is much smaller than the dimension. Let's consider a slight generalization of adversarial examples. Let's say we just had some extra data that someone gave us, but this extra data is correctly annotated. So that in the sense that like how the adversarial examples actually had the right label. So here the y and x extra data is actually related perfectly as per theta star. And sort of inspired by the zero training error setting, we study the two minimum norm interpolants. One is the standard estimator, which simply fits the standard data and is the minimum norm interpolant on the standard data. And one is the augmented estimator, which could be the robust estimator in adversarial examples, or more generally for any extra data, fits these extra data points as well as the standard points and is the minimum norm interpolant on these points. So we're studying how these two estimators are related, and when adding this extra constraint of the extra data could actually make your error worse. So here's a simple picture which provides intuition in this linear setting, sort of mathematically why this could happen. So one way to think of the minimum norm interpolant in this very simple noiseless setting is it basically recovers the theta star exactly in the span of training data because the constraints like give you that information exactly. And because it's a minimum norm, it is basically zero in the null space. So this exactly captures how these estimators look like. So here's a small visualization. So let's say your standard data had two-dimensional null space, E1 and E2, which we visualize here. So both the standard and the augmented estimator outside this null space like recover theta star exactly because X standard has that information. Now, let's say this is what theta star look like in the null space. So the standard estimator, which is the minimum norm interpolant, is basically just 0 in the null space because that has the smallest norm. Now, let's say we had this extra data which involves this direction. And so we're trying to fit theta star along this extra dimension when we do augmentation. So this is what the augmented estimator would look like. So along XEXT, it gets theta star exactly, and it is 0 perpendicular because that's the minimum norm interpolant. So these are the two estimators. But now we're actually interested in the test error of these two estimators. So the test error, the standard test error basically takes the following expression. So it is theta minus theta star, which is a parameter error, but it's scaled by this population covariance sigma. So this is what comes out when you write down X transpose theta minus X transpose theta star. So let's say this sigma had much higher weight along the E2 direction than the E1 direction. That is, let's say the errors in E2 direction are basically the most costly and determine the test error. Now let's look at what the E2 errors of the two estimators here look like. So the standard estimator is plotted here, and the augmented estimator is plotted here. So from this picture, we see that the augmented estimator, by fitting this extra dimension, XEXT, actually has higher error along the E2 direction, which is a different direction. And suppose the E2 direction was actually what contributed to the test error, then the augmented estimator has higher test error than the standard estimator. So this comes just because, like, by doing minimum norm interpolation outside of XEXT, the augmented estimator tries to do the minimum norm, but then that could increase the error along other directions. For example, the E2 direction, and sigma is what decides which directions are more expensive, but that's somehow not incorporated into the estimator. So here's an example where if sigma has higher weight on E2 direction, the errors are more costly, and the standard error is higher for the augmented estimator. So just to sort of the same intuition, sort of more mathematically, this is what the simple theorem looks like. So the difference in the errors of the two estimators takes the following form. So there is a V transpose sigma V term and a W transpose sigma V term, where W and V are basically the projections of the component of theta star in the null space, both along the augmented data and perpendicular to the augmented data. So just to make things a little simpler, so if you see that the one term that we have is always positive because sigma is PSD, and so that this captures the amount of error that actually decreases because we have incorporated some information along the direction of the augmented data, so that should decrease error in some way. However, there is this term W transpose sigma V, which could be negative. And that's sort of like, for example, in the previous example, when somehow the augmented estimator could be misaligned with sigma, and that could lead to this term being negative. And this could lead to the standard estimator having lower error. So there's sort of this, like, it's a more mathematical way of like looking at the same phenomenon earlier, where there is a decrease, but there's also an increase. And that's sort of why augmentation could actually lead to higher standard error. Sort of this theorem can also provide like some sort of simple conditions for when this is not, when this term over here is always positive and the augmentation always helps. So one thing is, of course, when this term W is 0. So suppose you like augmentation, you augment the entire space itself, then of course you have incorporated all the information that's possible and you are going to get 0 error. So if you have a perfect augmentation which spans the entire space, then there would not be any trade-off. Sort of another interesting condition from this expression when we wouldn't be trade-off is when sigma was identity. So if sigma did not have this effect of having some directions more important than the other, and we were just like isotropic, then here W and V are perpendicular. So this term would always be 0, and V transpose V is always positive, and augmentation always helps. So if you only focus on the isotropic case, then data augmentation always helps, which is sort of the conventional wisdom. But when sigma is not identity, we could have these cases where certain directions are more expensive, and hence data augmentation could make you do worse. So with that intuition, let's look at what we can do to mitigate the trade-off. So in some sense, we have already the same information as the standard data. So we should be able to at least not do worse than the standard data when we add this extra information. So how could we change the estimator? So one idea is that we want to fit the extra data, but in the null space, let's not do something too different from the standard data, because we know the standard estimator is already good. So let's try to behave just like the standard estimator on the null space of things we haven't seen, but let's also fit the extra data while doing so. So by fitting the extra data, we are improving robustness, but then we don't perform too differently from the standard estimator on overall distribution. So instead of relying on the minimum norm inductive bias, let's specifically regularize towards the standard estimator. Of course, we don't want to change the standard estimator because we know that already performs well. So pictorially, so this is the same setting as before. And let's say this is the standard estimator here. So now we have introduced this extra dimension that we want to fit. And we have this space of solutions in this gray over here, which is like all the solutions that fit this extra dimension. So among all of these things, we could fit anything. We could pick anything. And the inductive bias or minimum norm would have picked the orange thing that we had earlier, but that was bad in the direction of E2. So now suppose we knew that the population sigma, covariance sigma, has like a large weight along E2. What we could do is the following. So we look at the error that the standard estimator has along we look at what the standard estimator has along E2. So we know the projection along E2 by just using the standard estimator. And now we'll try to find a robust estimator that fits this extra data. But along E2, which is, we know, the more expensive direction, it basically behaves just like the standard estimator. So instead of picking the orange line, which was here, we pick this green estimator, which fits extra dimension, but does not increase the error along this E2 direction, which was expensive. So this is kind of what it looks like. So instead of having the minimum norm interpolation, minimum norm objective, we now have a term that regularizes towards the standard estimator, sort of regulated by sigma, because sigma decides which directions are more important. So we fit the standard and the extra data, but then change the inductive bias to regularize you towards the standard estimator. And this is exactly the green estimator in this figure, which does not see the increase in standard error that we had earlier. So the nice thing is, if we rewrite this objective on the top here and just like replace sigma by expectation of x transpose x, it takes the following form. So this objective is actually easier to interpret. So what it says is that you generate pseudo labels using a standard estimator on large amount of unlabeled data, and you train your estimator to be close to have predictions close to the pseudo labels while still interpolating the training data that you have. So this is kind of basically what the green line over here is doing, which mitigates the trade-off. So you try to behave like the standard estimator on a large amount of unlabeled data, but then you fit your standard and robust data on your training data as it is. And so this is basically the principle of robust self-training, which was also introduced like in some recent work for robustness. And the nice thing is that when you're trying to mitigate this trade-off, we ended back to this sort of similar algorithm that was studied earlier on robust self-training. And this provides some basis for why robust self-training might be a good idea to mitigate the trade-off. And it utilizes unlabeled data to get access to the sigma, because sigma, like we saw earlier, kind of plays a key role in determining whether augmentation helps or not. So we utilize this sigma information by having a large amount of unlabeled data, and then we perform robust self-training to help mitigate this trade-off, where we regularize towards the standard estimator on directions that we don't know. So just to specify the robust self-training procedure, it's a two-step procedure. So the first step is to train a standard estimator, just like normal. Don't incorporate any robustness information, and use this estimator to pseudo-label a large amount of unlabeled data. That is, you generate labels using the classifier on unlabeled data. And now you take the pool of labeled and your pseudo-labeled data and together perform robust training on this bigger data set. So this was actually, so in fact, even our group wrote a paper on robust training, but robust self-training, but we arrived at this at a different, we had a different objective of just improving the robust accuracy itself. And we thought of the pseudo-labeled, unlabeled data as a way of generating more samples. And so like, this could help with just robust accuracy. But interestingly, when we try to mitigate this trade-off with the standard and robust accuracy, we kind of end back at, we return to the same procedure of robust training. So we can think of robust self-training as basically having the 4 different losses as shown here. And this is sort of just to make concrete how it's related to the estimator from the previous slide. So this is what it looks like. So you have, so the first like term over here basically is fitting the label data, which is a standard data. And the second term here is fitting the extra data, which could be adversarial examples. And then these 2 terms involving the unlabeled data basically appear in the objective like we had earlier, where you try to match the predictions on the unlabeled data for your new estimator with the original standard estimator which you trained in step 1. And like we have the formal theorem in our paper, but informally, it says that for the same noiseless linear regression setting that we had earlier, you can prove that this new estimator, theta RST, which uses unlabeled data, gets the best of both estimators. So the standard error is never higher than that of the standard estimator, and the robust error is never higher than that of the robust estimator or the augmented estimator. So in some sense, RST achieves the best of both estimators in both the objectives. And in particular, there is no trade-off if you use RST. So you never increase your standard error by increasing a robust error in this noiseless linear regression setting by using the robust self-training estimator. And like for example, in the splines example, like from earlier, what RST would look like is the following picture on the right, where you fit these local perturbations, but now when you've generated pseudo labels on the rest of the line, you also fit those pseudo labels and you actually end up recovering F star perfectly when you do robust self-training. So the way we sort of solve this local and global fit issue is to basically fit the global structure using standard estimator, then use the standard estimator as an anchor to fit the local structure using robust self-training.
Hi, Aditi, I have a question.
Yeah.
So what happens in the noisy setting?
Yeah, so that's a good question. So I guess we didn't analyze the noisy setting in this case, in this paper. But so one thing is like this, all this analysis is exactly like the bias of the noisy case. But the variance would actually also increase when you do augmentation, because in some cases you're estimating directions which earlier you didn't have to estimate at all. So the variance could also go up. So yeah, so in for the noisy case, both the bias and the variance have to be analyzed separately. The bias analysis is exactly the same, but the variance also can go up when you do data augmentation. And robust self-training, like you have to be a little careful with sort of like for small levels of noise, you can prove that robust self-training improves the variance as well, but obviously not for large variance. And also minimum norm interpolation becomes a little questionable for noisy data. So if you have regularization, things could be a little different.
Okay, thank you. And there's another question. Does robust training completely erase or minimize the inductive bias?
Right. So I'm assuming this meant robust self-training?
Yeah, I think so.
Yeah. Right. So yeah, so robust self-training. So one observation is that the inductive bias of standard training is good because that is why things work well. So robust self-training is trying to change the inductive bias to match the inductive bias of standard training. So you try to behave like the standard estimator did because that somehow did well in practice. We know that that works well on the average distribution. So you try to change your inductive bias to match the inductive bias of the standard estimator. So for example, in this picture here of splines, the inductive bias of the standard estimator makes you learn this simple linear function. But then if the inductive bias of just the augmentation is bad and it gets you to this slopey down line. But then now we change the inductive bias to basically look like the inductive bias of the standard estimator, and hence you get this linear structure.
Okay, thank you.
Yeah, thanks for the questions. So I guess just for the interest of time, I'll go over this very quickly, but basically with two different kinds of robust training methods, using robust self-training would improve both the standard as well as the robust accuracy over the supervised counterparts. So of course it's not perfect. So we kind of bridge the gap a little bit. We're still far from matching the standard accuracy, and even the robust accuracies are quite low. So this is still a very important open problem. And just to note, it's not just a case of having more unlabeled data. You need to use this pseudo labels or the standard estimators. If you try to do something without using the standard estimator, your standard accuracy in fact gets even worse. So sort of like the analysis earlier suggested, changing the inductive bias to match that of the standard estimator is sort of what's key to using unlabeled data to improve performance. Quick summary. So the empirical observation that's kind of interesting is that adding valid data, you have to be careful because it does not always help. And we sort of analyzed a simple linear model that kind of explained why this could happen. And that taught us that inductive bias plays an important role, and we could try to regularize an estimator towards a standard error. And this sort of suggested robust self-training, which does work quite well in practice to improve both, but it's not complete. And it's still I think it's still a very interesting open problem as to how do we actually match the standard accuracy or even improve the standard accuracy while also being robust. So I guess with that, I'll switch quickly to the next part of the talk, which is on spurious correlations. Are there any questions on the previous part? Okay, I guess Surabhi will interrupt me, so let me move on. So like we said earlier, like the chest X-ray example, models can
Aditi, I'm going to stop you. So there's a question, is this analysis only for linear models?
Yeah, the analysis is only for linear models. Okay, it also works for kernels, so you could consider like phi of X instead of X, but it is only for linear models, yes.
Okay.
Yeah, thanks. Yeah, so like the chest X-ray example, we know that models can latch on to spurious correlations. So here's a sort of more easy to understand example. So let's say our goal was to predict whether this is a land bird or a water bird. So the ML model has to predict the bird type. And So one way that the model could do well is basically just look at this background, which is a spurious correlation. So if it looks like a water background, then the model could say that it's a water bird. So this works well on most of the examples. But if we take this poor water bird and place it in a land background, like the following image, the model continues to use the spurious correlation and hence predicted it's a land bird and getting it wrong. So how do we solve this problem? Okay, so here's another example. Let me skip this. So formally, how do we think of the spurious correlations? So there could be several ways to do so, but one formalism as follows. We group the data set into 4 different groups, depending on whether the spurious correlation, which in this case is the background, matches the label or not. So for example, on these diagonal instances, for majority of the examples, the background matches the label, that is a water bird in water or land bird in land. But there are a few examples where this correlation is not observed and things are flipped. So those are the minority examples. So among these groups, let's see how the model does. So if we just minimize the average error, the average performance is actually quite good. So the average error is 0.03 because on majority of the examples, the model performs well. However, there are these groups which are the minority groups where the spurious correlations are absent and the worst group error is quite high. So because the model is relying on the background, it gets things wrong. For example, this water bird in land background. So the worst group error is large. So this sort of formalism of the spurious correlation problem, where we split the data set into groups depending on whether the spurious correlation is absent or not, is nice. Because if we minimize the worst group error, then that says that the model is not relying on the spurious correlation. So what are the approaches for improving the worst group error? The one sort of natural approach is to just minimize the worst group error on the training set, which is like the distributional robust optimization settings. So instead of minimizing average error, we minimize the worst group error, which is what we are interested in. Sort of the other proxy, which is quite simple but very related to the DRO, is like we have this group imbalance. And so what we would do is like naturally, if the groups are small, you want to increase their weight. So you reweight the groups such that smaller groups have larger weight. And hopefully this is sort of usually what people do for class imbalance, and this should also help in this case. So these are 2 approaches that we could think of for improving the worst group error when we sort of specify this spurious correlation problem in terms of the groups. But the problem is both these approaches actually fail when we have high capacity models. So if we don't do any regularization and use really large models, what ends up happening is that even if we do this sort of upweighting or minimizing the worst group, only the average error goes down and the worst group error is really large because the model still relies on spurious correlations and gets the minority points wrong. On the other hand, if we had a low capacity model where either we had a lot of regularization or we reduce the model size, we end up getting both average and worst group error. That is, you get good performance on all 4 subgroups, which means that the model is not relying on the spurious correlation. So interestingly, the approaches for improving worst group error show that the high capacity models are actually still bad because you can't improve your robustness to spurious correlations by these methods that we know. On the other hand, low capacity models actually do quite well. So just digging into this a little more. So if we look at the average accuracy of empirical risk minimization, so there is this famous double descent curve where explicit complexity control does not increase the test accuracy. For example, here is this plot from May and Montanari, where as you increase the x-axis here is sort of the degree of overparametrization. So as we make the model more overparameterized, the accuracy actually goes down. The accuracy actually increases in the sense that the model gets better with larger and larger models. And so complexity control is not necessary for improving test accuracy. So this is usually what we know from standard accuracy and ERM. However, when we look at the worst group error of DRO or these upweighting methods, which try to improve robustness to spurious correlations, we find that we need explicit complexity control. So this could be many ways, either weight decay or early stopping or decreasing the number of parameters. So one of these things is necessary in order to improve the worst group error. So here are sort of the empirical results. For example, on the water bus data set that we had earlier, so we do have a double descent curve, but the overparameterized regime has higher worst group error, which is this blue curve, than the underparameterized regime. So the best error occurs in actually a smaller model, which is the exact opposite or a stark contrast to what we know for average accuracy, where larger models or no regularization still works quite well, and in fact could work better. So this is kind of interesting as to like why the trends are reversed in this case. So just like a quick summary of the slides that we had earlier. So somehow the worst group error has this interesting shape where the overparameterization is worse, But the average accuracy, both for the either DRO or upweighting or just ERM, follows this double descent kind of curve where at the overparameterized end, the error is lower. So why does overparameterization, which helps standard accuracy, make the worst group error worse? So here's like a story for why, this like one way to think of this. So let's say each input has both core and spurious features. So the core features are actually what help the label prediction, and they work across all groups. But spurious features are easy to learn, but they only work on the majority groups. For example, using the background is very simple. You just look at the color of the background. You don't have to know anything about the semantics of the birds, but they only work for majority examples, not for all the examples. On the other hand, learning the actual bird component could be hard, but then it works on all groups. So in this setting, ERM, as we saw earlier, uses only the spurious features and gets very low accuracy on the minority groups. So it ends up getting zero training error, but it does not do it in a way that actually translates to test error being low on the minority groups. Similarly, when we do reweighting, only small models seem to actually benefit from the reweighting. So they use the core features, which is why they get small worst group error across, and all groups perform well. But when we use larger models, we have the same problem as ERM, where it ends up using spurious features on the majority groups. The minority groups, it does something, but it does not use the core features and ends up using more the spurious features and memorizes the minority. We say memorizing because the zero training error does not actually translate to low worst group error in the test set. And on the test set, the model still uses this spurious feature and gets good average error, but really bad worst group error. So here's a toy sort of model that allows us to analyze this formally. So let's say we had a very simple setting where the core feature is just a scalar, and we had two labels like either -1 or 1, and the core feature is related to the label. So it's like for example, it's related to the bird type. Then we could have a spurious attribute, which is like the background, and the spurious attribute detects the spurious variables, the spurious features basically. And we can vary the model capacity by having these noise features, so which is basically high dimensional Gaussian, which is scaled in some appropriate way. And as we change the number of noise features, we could change the model capacity. And then we learn a linear classifier on this concatenated input, which has core features, spurious features, and noise features. And we want to study the effect of increasing the dimensionality of the noise on how the classifier uses either the core or the spurious feature. Just like before, on majority of the points, the spurious attribute and the label are the same. For example, the water bird on a water background. But there are some minority points where the correlation is reversed. So the spurious correlation is not present on the minority points like the majority points. For example, the water bird in the land background. But these are much fewer than the majority points. So in the overparameterized regime, where the number of noise features is really large, when we do this reweighting, or if we didn't do the reweighting, the minimizer is always the max margin classifier. Because in the zero loss, when you can fit the training points exactly, when things are so high dimensional, your reweighting doesn't change anything because the loss is still zero. And the max margin classifier is what is learned by either through ERM or through reweighting. But in the underparameterized regime, when you can't fit all the training points to get zero loss, the reweighted estimator is a unique minimizer of the reweighted logistic loss, which is basically where the minority points have larger weight on the logistic loss. So these are the two extremes that we're interested in considering. One is sort of why does the max margin classifier do so badly, and how the reweighted estimator in the underparameterized regime performs well. So here's a pictorial representation. So recall that we had only two dimensions which we actually cared about, the core features and the spurious features. So the two extremes that the model could do are plotted here. One is the model uses the core feature and gets this vertical line, or the model could use the spurious feature and get this horizontal line. So let's look at the vertical line here. So, so the crosses are the minority points. And since the minority points are upweighted, now the model is incentivized to actually get these points on the right side of the boundary. And the underparameterized model, because of the reweighting, actually learns this boundary on the left. On the right, because it gets the points wrong and they're upweighted, the mod it's not going to be the minimizer of the logistic reweighted logistic loss. So the underparameterized model actually learns the right thing. But what happens in the overparameterized model is very different. So because we can obtain zero loss in many ways, the norm of the resulting zero loss classifier, or the inductive bias of the minimum norm, actually plays a key role. So let's go back to the two extremes before. Now the difference is that even on the right, it can get zero training error by sort of memorizing, which is kind of represented by these small blobs around the minority points. So it can use the noise features to fit these minority points, even though it is still using only the spurious feature on these 2 dimensions. And it turns out that, in fact, the thing on the right has a lower norm, where it uses the spurious feature on majority of the points and memorizes the minority points by using the noise features. So this is sort of special to the overparameterized regime because you can actually memorize. And so the reweighting doesn't help at all because you still get these loss, but then you get it to a very different way of using spurious features and simply memorizing the minority points. This sort of captures the intuition as to why underparameterized models work well, but overparameterized models suffer a lot. And that's because the norm of the solution is sort of much higher for the, is much lower for this case where you memorize the points. But why would that be so? So why is the norm lower in this case than the example here? This is just a theorem that kind of says the same observation earlier, but formally. So I wouldn't worry about the constants. These are just like this could be any constant. But basically the majority fraction, the number of majority points has to be much larger than the minority points. And let's say that the core feature is more noisy than the spurious feature. This is our proxy of trying to say that the core feature is harder to learn, for example, the bird, than the spurious feature, even though the core feature works on all groups, but the spurious feature works only on the majority groups. So in the highly overparameterized setting, the worst group error you can prove is actually worse than random in this setting. Just to parse the conditions, the first condition says large majority fraction, and the second condition is saying that the spurious feature is less noisy than the core feature, or easier to learn than the core feature. So when these 2 conditions are true, you can prove that for overparameterized models, the worst group error is really large. In contrast, so here's a particular instantiation of the same settings. So in this case, say when spurious variance is 0, sigma core is 1, and in the underparameterized setting where there are no noise features, you can prove that the worst group error of the reweighted estimator is small and less than 1/4. So this is like a provable example where the underparameterized regime does much worse than the overparameterized regime. So here's the proof sketch. So recall that we had these 2 core and spurious features like before. Let's consider 2 simple extremes. So in the overparameterized regime, we are concerned with all estimators that get 0 training loss, and we want to see which estimator has the lowest norm. So one extreme could be if the classifier used only the core feature and did not use the spurious feature at all. However, since the core feature is somewhat noisy, if the classifier has to get 0 training loss, it has to fit the rest of the, some constant fraction of the misclassified points using the noise features. Because that's the only way it can get 0 training loss, because the core feature is somewhat noisy. And so like some constant fraction of majority and minority points, you have to use noise features. Other extreme is when a model uses only the spurious features. But now, since it uses only the spurious features, the spurious feature is less noisy, and the classifier can get 0 loss on the majority with high probability by using the spurious feature. But on the minority, of course, the spurious feature is not present, and therefore it has to use noise features for the minority points. But now when we compare these 2 extremes, so we see that suppose the majority fraction is really large, that is majority is much larger than minority. The first option requires memorizing a larger number of points than the second option, that is using noise features on a larger number of points than the second option. And in fact, this was a condition that we had from before. And so the reason this is true is because the norm of the classifier scales with the number of points that have to be memorized. So in the first case, the norm is larger than the second case because the number of noise points for which you need to use the noise features is actually much larger because the majority points you have to use the noise feature. Whereas in the second case, the majority points are all easily fit using the spurious feature, and we needed the noise only for the minority points. I'm running out of time a little bit, but just very quickly, why does the noise matter? Why does the memorization matter in the norm? So by representative theorem, we can write the noise component in the following way. So for very large n, these noise features are essentially almost orthogonal and have a similar norm. So the norm of the noise component depends on the number of points for which this alpha I is large. And in some sense, if alpha I is large, the point is memorized. So as we have more number of points for which alpha I is large, the norm of the noise scales, and the model is incentivized to memorize as few points as possible, which in our setting corresponds to using the spurious features on the majority points and memorizing only the minority points because the minority are so few. So there were 2 contributing factors. So one was the majority being much larger and the spurious feature being much easier. So the interesting thing is this theory suggests that if we reduce the number of minority points, we removed a lot of we reduce the number of majority points by removing a lot of the points, then we reduce the memorization cost associated with using the core feature. So that should actually help, because we can't change the second part because that is inherent. So if this is true, then one potential fix for using large models and still getting good performance to spurious correlations is very unintuitively, but throwing away a large number of majority points, that is subsampling. So we reduce the majority points enough to make them really close to the minority points. And by removing a lot of points, we can actually get good performance according to the theory. So does this actually work in practice? And surprisingly, we find this actually true, because even in some of these data sets, the group imbalance is so large that we throw out about 99% of the majority points. But like once we do that, we find these curves where we get basically the average and worst group error to be very similar to what we know of the PRM or the double descent curve that we saw earlier, where overparameterized models work well and they work better than underparameterized models. So subsampling helps overparameterized models achieve low worst group error. So just to compare the two approaches, initially we looked at reweighting, where we had all the data points, but we changed the weight on the points. But in subsampling, we literally remove large number of majority points and we remove points to make them balanced. So in the first case of reweighting, the curve we see is the following. For the worst group error, the overparameterization is worse. But now when we do subsampling, we get back the curve that we know from before, where overparameterized models work better. Interestingly, sort of the best performance in both cases kind of match each other. So the smaller models on this case and the larger models on this case are pretty comparable. But it's unsatisfactory in that we sacrifice expressivity in the first case, or we sacrifice majority data. So clearly this is not a great solution. And this is again another interesting open problem, like how do we get the best of both? How can we use large expressive models, but also use a large amount of data without sacrificing a lot of statistical information that is there in the majority data to do well?
Aditi, there's some questions.
Yeah.
So would appropriate weight decay also get worst case group error?
Yeah, that's a good question. So in our paper, we have experiments to show that L2 regularization as well as early stopping, both of them, when used with reweighting, also behave similarly to like changing the number of parameters. So that's another complexity control that would help. Yes.
Also, are there like connections to fairness literature here, that like something that you can borrow from that line of work?
So I don't think anyone in fairness has looked into the effect of actually changing the model size, but things like upweighting or like change, like I agree that the objective is actually very similar to fairness. And in fact, I think this thing has fairness, what do you say? You can use this for fairness in the sense that it says that for being more fair, you actually should use smaller models. So yeah, as far as I'm aware, I don't think people have looked at the effect of model size in fairness, because a lot of the theory focuses on really simple sort of under parameters models, and some of the experiments focus on these like representations and things where they don't really look at changing the number of parameters.
Yeah, thanks.
Yeah, thanks. Yeah, so sort of just a quick summary, like the empirical observation, which is interesting, is that bigger models don't always help. For example, for the worst group error. And the simple model, when we analyzed, sort of said that this is because there is again this inductive bias rule that says that we want to memorize as few examples as possible. And so if you force yourself to get zero training error, then memorization can come into picture and can force you to use spurious features. And so that suggested two fixes: either remove the memorization completely by either using underparameters models, or we reduce the number of majority points by throwing away majority points and kind of balancing this memorization cost. And that suggested either subsampling or underparameterization, and both of them sort of work in practice, but are of course unsatisfactory because you are sacrificing something. And so just to pop back up and sort of conclude both the threads, of course, robustness is a serious problem in real world applications, and we have made progress as a community towards making things more robust. But the problem is that robust accuracy does not always track standard accuracy. So this is like kind of has practical considerations, but it's also an interesting research problem. For example, robust self-training came up as a fix that helps to some extent, and similarly, complexity control or removing data again helps to some extent. But both of these, I think, are interesting open problems, like what can we do to actually make things better? There's still a lot of gap. And in the technical side, we studied robustness in the linear settings, and we saw that even simple linear settings revealed some core insights. And it suggested that we need to rethink data augmentation, and we kind of need to rethinking generalization, in the sense that complexity control could still be very important in cases of robustness. But as the community as the general ML community looks at developing more powerful tools to study interplay between all these like optimization, inductive bias, generalization, and going beyond linear settings, I think it's also interesting to see that maybe studying robustness in addition to the standard accuracy could lead to richer insights into understanding all these components. With that, I'd like to thank all my collaborators as well as all the organizations that have funded this research. Yeah, thanks. If people have questions, then I can take them for the next few minutes, I guess.
Thank you so much for the great talk. Now I'll allow people to unmute themselves so they can write on the chat if they have a question.
Sorry, should I be looking at the chat, or are people going to be asking?
I'll monitor the chat, don't worry.
Okay.
Hi, Aditi, I have a question.
Yeah.
So it seems that understanding these phenomena in the linear setting is tractable, but beyond the linear setting, even in kernel or like, even if there's a nonlinear feature map, it seems that some analysis becomes intractable.
Right.
So do you have any comments on like how can these results be robust to the model? Yeah.
Right. So I think, yeah, that's a great question. But sort of my thoughts are that maybe some of the because at the end of the day, we can't exactly analyze something that is realistic and that we're going to deploy. So the question is like sort of what models are tractable but still capture sort of the intuition that can be useful in practice. And it feels like in that sense, it was kind of interesting that even linear models like gave us some insight that we didn't know starting off to, and that could actually translate to something in practice. So I feel like as long as we are in a setting where that is true, where there's no real like serious mismatch between what we think and what we observe, like it's still promising to look at linear models. But like as analysis techniques and stuff get like more advanced and people are like looking at different models, hopefully we can borrow those ideas to robustness, and maybe there are richer insights that could come through that. But yeah, I think both robust accuracy as well as standard accuracy suffers from the same problem, that it is hard to analyze more complex models. But yeah, but like for example, your work also shows that like maybe even like analyzing random features or simple models could still capture like most of the intuition that kind of explains some of these things in practice.
Thank you for your comments.